Hello, in this video today we'll be covering a very hard integral, well, in terms of hard, a very hard integral to integrate. So today's integral, we'll be evaluating this integral, the integral from 0 to infinity of sine x over x. Now there's a couple of ways you can evaluate this integral. You can use it using the Laplace transform, Feynman's technique of integration, but today we're going to do it basically using complex analysis. I don't know how to spell analysis. That's really embarrassing. Let's just rub that out. Okay, so complex analysis basically takes whatever a really hard integral, we go into the complex plane and we work out an expression for our integral in terms of complex numbers, and then we evaluate it from there. So what we do is we basically take a look at this function here and we replace it with a function of complex variables. So we have f of z, and we replace our sine x with basically e to the I of z and replace the x with the z, okay? And now we're going to integrate this function in the complex plane. So we're going to draw a little Argand diagram with our imaginary axis and our real axis, okay? And basically we're going to integrate over a contour. Now a contour is basically a bounded region. So when we integrate a contour, we use a special integral. So we have this integral symbol and then we have a little circle here to integrate a contour. And we're going to integrate over a particular path in the complex plane. Because in the complex plane, if you integrate between 2 points, you have to choose a specific path. Let's say you want to integrate from here to here. There's an infinite number of paths you can pick. So you have to specify your particular path. So how do we do this? So let's take a look at this function here. So obviously there's going to be a singularity at 0, 0 pretty much, okay, because of this little z on the bottom. So basically we're going to start is we're going to integrate from 0, from basically 0, from negative r, and you're going to integrate along the real axis to this point epsilon here. So we're going to have negative epsilon. And then to avoid this singularity here, we're going to integrate over this little path here to epsilon. So negative epsilon and epsilon are like really small numbers, infinitesimals basically. And then you're going to integrate to a point r, so it's a really big number. So r and r are basically like negative infinity and positive infinity. So you're going to integrate to there. Then we're going to close our contour and integrate along here all the way back to r. So we're going to integrate along here, this particular path, and this is going to be called capital gamma, and this here will be little gamma, okay? So if we integrate along a contour in the complex plane, because since this function here is analytical, if you integrate an analytical function over a contour, it's going to be equal to 0. This is via Cauchy's integral theorem, but I'll make that in a separate video. So we know this is basically true about our little diagram here, but we can actually break up our little contour integral into its parts, because we can have an integral from here to here, from around here, here, and around there. So we can actually rewrite this part here as basically, so the contour integral over the path c of e to the I z divided by z dz is equal to the integral from negative r to negative epsilon, and we basically just put that as our bound. So we have negative r to negative epsilon, and since we're on the real axis here, when we're integrating here, we can replace the z's with x's. So we have e to the I of x divided by x dx. Then we integrate along from negative epsilon to epsilon over the path of gamma. Now notice on this path here, gamma, we're in the imaginary plane, so we need to use imaginary numbers again, so z. So we integrate from negative epsilon to epsilon e to the I z over z dz, okay? Then we integrate from epsilon to r, so we're back on the real axis, so we can use x's again, so we integrate from epsilon to r e to the I x over x dx. And now finally we integrate from r to negative r along the path gamma. So we integrate along the path capital gamma e to the I z, so we have to use z because we're in the imaginary, we're in complex plane again, divided by z dz, and this whole thing is equal to 0. Now what we're going to do now is basically, what we do to basically integrate this function here is we set up our little complex integral here over a contour, okay? So we've done that. Now basically we've got to turn this expression we've gotten here into basically sine x over x. Now the way we do that is basically we're going to get all of our real parts on one side and all of our imaginary parts on the other. So let's just take a look at what our imaginary parts are. So we have this integral here and this integral here. So we're going to move both of them onto the right hand side of this equal sign. And we're basically just going to flip it. So we're going to rewrite it as basically, alright, so this is equal to the negative integral from over capital gamma e to the I z divided by z dz minus the integral of negative epsilon e to the I z dz over z dz is equal to our real parts, which is negative r to negative epsilon e to the I x over x dx plus the integral from epsilon to r e to the I x divided by x dx. Okay, now let's move this a bit down. Alright, so for now we're just going to ignore this side for a bit and we're just going to sort out this side over here. Okay, so notice these two integrals we have here are they're very similar in terms of their bounds. So we're going to try and combine them together using a dummy variable. So what we're actually going to change pretty much is we're basically going to change this little integral here, okay? So let's just take a look at that. So let's just say the integral I is this integral here, so negative r to negative epsilon e to the I x over x dx, okay? How are we going to turn, we want positive epsilon down here and a positive r up here, so we can combine it with this integral here. What we do is basically we do this little mathematical trick called a dummy variable. Now a dummy variable is very powerful, and the fact that we can change this integral to pretty much how it looks, because whatever this integral evaluates to, it will be independent of whatever variable we have here. So it doesn't really matter what variable we have. So we can just say, all right, let x equal negative v. Therefore, dx over dv is equal to negative 1. Therefore, dx is equal to negative dv. Now, how does this help us? So all we're going to do is make our substitution. So if we say, all right, negative r is x, therefore the v version of that is going to be positive r. So we'll have r down here. So this is just transferring this into terms of v. Negative epsilon is our x, so the v version of that will be positive epsilon. We're going to have e to the I multiplied by negative v, divided by negative v, then multiplied by negative dv, okay? So just fixing that up, we're going to have the integral from r to epsilon over e to the negative v over v dv, because the negative here and the negative here cancel out. Okay, and of course we're going to switch the bounds, so we have to put a negative sign at the front. So we have the negative of epsilon to r e to the negative I v dv. Now, since this is a dummy variable, whatever this integral evaluates to, it will be independent. So it doesn't really matter what variable we have, so we can just change these v's back to x's. So we can just say, all right, this is just going to be the integral from epsilon to r e to the negative I x over x dx. Okay, now that helps us a lot, okay? So now we're just going to move this, and we'll make this a bit smaller and move it to the side for a second. So now we're going to replace our integral here. So we'll have, let's move across for a bit. So we're going to have the negative integral from capital gamma e to the I z over z dz minus the integral of negative epsilon to epsilon e to the I z over z dz. And then we're going to replace this integral here with this integral we have here. And notice they're the same bounds now. This integral has the same bounds as this integral, so we can actually combine them together. Oh, there's a negative sign there, and that's negative I. So what we have on our right hand side is the integral from epsilon to r is equal to basically e to the ix minus e to the negative ix all over x dx. Fantastic. Now that we have that, this is really good for us. So I'm just going to move this down here for a bit, and we're going to go to the side and down again. Alright. So the reason why this is really good for us is because the definition of sine x in terms of complex numbers is e to the ix minus e to the negative ix over 2I. That's why it's really good for us. You can see we've almost got sine x here. So all we have to do is put this 2I up here. So we'll have 2I sine x is equal to e to the ix minus e to the negative ix. Now we can make this substitution here into here. So therefore, we're going to have, let's just move this to the side, all of it. So now we're going to have this integral, so we'll just write the left-hand side real quick. So the integral negative gamma e to the iz over z dz minus the integral of negative epsilon to epsilon e to the iz z dz. It's basically going to be equal to 2I, brought that out the front of the integral because it's a constant, from epsilon to r of sine x over x dx. So that's the reason why we basically went into the complex plane. So we could basically get an expression for sine x in terms of complex variables. Now this is almost our integral. So recall our integral is 0 to infinity of sine x over x. So basically the way we basically turn this into that is basically we're going to apply a limit. So basically we apply the limit. So the limit as r approaches infinity, and the limit, as r approaches infinity, and we don't need to write limit twice, and as epsilon goes to 0, and we have 2I, the integral epsilon to r of sine x over x dx. Now if we're applying this limit to one side, we also have to apply it to these ones, these integrals here. So we'll go equals the limit. Since this integral here only depends on r's limit, so we can only write the r limit for this one. So we have the limit as r goes to infinity, because this integral here doesn't have any epsilons in it, so the epsilons won't affect it. So limit as negative integral from gamma of e to the iz divided by z dz, plus the limit as epsilon goes to 0 of the negative integral from negative epsilon to epsilon e to the iz z dz. Now, knowing off the top of my head, this whole integral here basically goes to 0. I'm not going to show that in this video because then the video would be like 30 minutes long, but I will make it another video. So this whole term here will go to 0 as r goes to infinity. So what we're actually left with is, if we just move this down a bit, it's basically we're going to have, so we now have 2I over the integral. If we apply this limit to this integral, we're going to have 0 infinity sine of x divided by x dx is equal to the limit as epsilon goes to 0 of the negative integral of negative epsilon to epsilon e to the iz over z dz. Okay, so we have our integral we want on this side, but this looks absolutely yucky as. How are we going to do this? Basically, the way we're going to do it is we're going to make a little substitution. So we're going to let z equal epsilon e to the I phi, okay? So if we differentiate that with respect to phi, so we have dz d phi, we're going to get I phi epsilon e to the I phi. So therefore dz is equal to I epsilon e to the I phi d phi. Oops, that is a terrible way to write phi. Okay, so now what we'll do, we're going to substitute this bit up here and in here, and we're going to substitute this bit in here. The reason we're doing this is because it'll make it so much easier to apply this limit that we have here. So if we make this substitution, so we have the limit as epsilon goes to 0 of this integral here. So if we apply this substitution, we're going to have the limit as epsilon goes to 0. Alright, so first of all, we need to change the bounds as well. I forgot about that. So if we go basically change the bounds. So let's say, alright, z is equal to negative epsilon. So let's change this bound first, so negative epsilon. So we're going to have negative epsilon is equal to epsilon e to the I phi. Cancel the epsilons, we're going to have negative 1 is equal to e to the I phi. How are we going to work that out? Well, recall Euler's formula. So e to the I x is actually equal to cos of x plus I sine of x, okay? So we can replace this bit here. So we'll have negative 1 is equal to cos of phi plus I to the sine phi. Now, basically now you just got to think of what values of phi can this take for this to be true. So we know that if phi is equal to, let's say, 0, cos here will be, cos of 0 is 1. So, and if we have 0 here, this term will go to 0. If we have cos of pi, this term here will be negative 1. And if we have cos of pi, if we have sine of pi, this will be 0. So the answer for this is basically phi is equal to pi. That's a funny way to say it. Alright, so that's our bottom bound that we've changed so far. What about our top bound? So our top bound was epsilon, wasn't it? So now we got to change it. So z is equal to epsilon. Therefore, epsilon is equal to epsilon e to the I phi. So therefore, 1 is equal e to the I phi. And then 1 is equal to cos of phi plus I sine of phi. Now, what phi value can we think of for this to be true? So if phi is equal to 0, this term is equal to 1, and if phi is also equal to, sine is equal, if we have sine of 0, this is equal to 0. So therefore, phi is 0. Okay? So now we can put in these new bounds. So we have negative, so our bottom bound here is pi, and our top bound is 0. And then we have e to the I, and our z is this thing here. So we'll have epsilon e to the I phi divided by epsilon e to the I phi multiplied by I epsilon e to the I phi d phi. Now you're probably thinking that's an even crazier integral. How are we going to ever work that out? Well, you don't really need to, and it's not that hard looking. I'll show you why in a second. Once I just move this to the side, because this is really like annoying me. Oh, bloody hell. Let's just move that. Make that small and move that to the side. So that's just our change of bounds. So if we take a look here in our integral, you can see that these terms cancel here, okay? And you're probably thinking, oh, what about this thing here? Well, if you apply this limit to this term up here, this will actually, as epsilon goes to 0, all of this will be equal to 0, and then e to the power of 0 is just 1. So this whole integral is just equal to negative integral. When you apply this limit, is equal to negative integral from pi to 0, I d phi. And we're going to switch our bounds, so we're going to have, that's going to be integral from 0 to pi I d phi. Now we can integrate that, so that's just going to be I phi, 0 to pi. So that evaluates to basically pi I. And this whole thing here is equal to 2i over the integral from 0 to infinity of sine x over x dx. That's equal to pi I. Divide both sides by 2i. The i's cancel. So we have sine x over x dx is equal to pi over 2. And that is true. Alrighty, that was tough. It's definitely one of the tougher integrals out there. I'm going to make another video on why this term here goes to 0, but just the explanation for this bit here is just so long and this video would go on for ages. So yeah, that's it for this video. So we go up here. Pi over 2. Boom. Alright, I hope you enjoyed this video and learned something. If not, if you have any questions, leave some in the comments and I'll try my best to answer them. More videos like this will be coming soon. Alright, thank you.